All right, we are going to talk about empirical formulas. Very much math-heavy concept, so hopefully your calculators are ready and you have enough battery power. First part, looking at calculating the percent composition. So looking at it, how much of each element is in each compound. Need to figure out the total molar mass of the compound. We all know how to do that one. And then looking at each individual element, take the element's molar mass divided by the compound's molar mass times 100. So for magnesium, carbon, and oxygen. And the whole thing should add up to 100. Sorry, the bottom kind of got cut off. I'm not sure why. So, an empirical formula. The lowest whole number ratio of atoms in a compound. They are going to be whole numbers, obviously. Molecular formula is the true number of atoms in each element in the molecular formula. So empirical and molecular are related by some factor. So our molecular formula, again, is just the empirical multiplied by some factor n. So for example, our molecular formula of C6H6, which is basically benzene, its empirical formula is CH, and n is a value of 6 that distributes throughout the entire compound. Again, simply stated, the empirical formula of benzene is just CH. So, formulas of ionic compounds are always empirical. It's the lowest whole number ratio. So a few examples: sodium chloride, you're not going to write Na2Cl2. It's always a 1-to-1 ratio of sodium atom to chlorine atom. Magnesium chloride, always a 1-to-2 ratio. You wouldn't write Mg2Cl4. Lowest whole number ratio always. 2 aluminums to 3 sulfates, 2 potassium to 1 carbonate. So ionic are always empirical. Most of the stuff we're doing now is going to be covalent compounds, where the ratio, you change the number of atoms, and the ratio stays the same, but you change number of atoms, you're going to get a completely new compound. So, looking at our molecular compounds, which are usually covalent, they might be empirical. Some are, some are not. For example, water is just H2O. You can't get anything simpler than water. But if I look at this guy, C6H12O6, which is commonly called what in your blood? Glucose. By what factor can we remove from this compound? Hopefully you realize you could remove a factor of 6. C12H22O11. No idea what this is. Is there any factor that can be removed? Nope. Good job. So how do we determine our empirical formula? We're going to always assume we have a 100-gram sample of our compound. With this assumption, it makes life so much easier. Then we do the rhyme. This will probably help most of you solve these problems, and if you just memorize the rhyme, it makes life so much easier. So we're going to do a percent to mass, mass to mole, divide by small, multiply till whole. So because we are assuming a 100-gram sample, the percent is just the gram number. Erase the percent sign and put a gram number, because the percent has to add up to 100%, and the grams of each element would have to add up to 100 grams. Converting on number 2 from mass to mole, just using molar mass, and then divide by small. Well, of all the elements in your compound, whichever one has the smallest mole number, you will divide all elements by that mole number. And lastly, multiply till whole is an if necessary. You're not always going to do it, But for example, when you divide it by small in step 3, if the value is 1.5, you need to make it a whole number. So 1.5 times 2 is 3. Key point here, if you multiply till whole, you have to multiply all elements by the same factor. Even if they don't need to be multiplied to make a whole number, if one of them does, you must multiply all numbers by the same factor. So let's do an example together. We want to figure out the formula of a diptic acid. It's 49, you guys can read this, why am I telling it to you? So step 1, percent to mass, and then mass to mole. So percent to mass, again, are all our percents up there in the question, are the mole number, or are the gram numbers. So 49.32 grams of carbon, 43.84 grams of oxygen, and 6.85 grams of hydrogen. So here we can convert carbon to moles, we can convert hydrogen to moles, and we can convert oxygen to moles. Again, sorry that the 16 at the bottom there got crossed out, but at least we now have our mole numbers. Looking at these three, which one is the smallest mole number? So here we go again. We're going to take moles of carbon from the previous step and divide by oxygen's mole number. And then we're going to divide hydrogen by oxygen's mole number. And then we're going to divide oxygen by oxygen's mole number. So here we are, our three numbers. At this point, these numbers are supposed to represent your subscripts in the empirical formula. However, as you can see, we have a bit of a problem. They're not whole numbers. So if we go to step 4, we must multiply by some factor to make it whole. So if we multiply carbon by 2, therefore everything must be multiplied by 2. If you notice in the middle with hydrogen, on the previous page it was 1.47. We will round to make it to a whole number. There will be a lot of rounding here. Whole numbers are what we want. So now that we have multiplied till whole, we are going to use these numbers as our subscripts in our empirical formula. So the original question is, what is the empirical formula of a diptic acid? C3H5O2. Pretty straightforward. Percent to mass, mass to mole, divide by small, multiply till whole. Again, if you do not have to multiply till whole, you are done at step 3. And the numbers you get at the end of step 3 are the coefficients of your empirical formula. Well, let's go one step further and solve for the molar mass of a diptic acid and figure out the molecular formula. So they give you the molar mass is 146 grams per mole. What is the formula? So I need to find the molar mass of the empirical formula. So from the previous slide, the empirical formula, C3H5O2. Solve for the molar mass. Pretty easy. You guys have done that with a periodic table. Now I'm going to go and divide the molecular mass given above by the empirical formula mass. So molar mass given, 146, and the empirical mass, we calculated at 73. Divide those, you get a factor of 2. Well, multiply the empirical formula by this number to get the molecular formula. Basically, 2 is the N term from a few slides earlier. And here we have C6H10O4. This is the molecular formula of a diptic acid. Please write down any questions that you may have to come to class tomorrow with. We will go over some more examples in class together, other practice problems. But if this seems relatively easy, it really is. Okay, combustion analysis. doing combustion analysis only changes step 1 of the rhyme. So instead of doing percent to mass, we have to solve for the mass in a different way with a different method. However, once you have the mass of each element, the rest of the rhyme, mass to mole, divide by small, multiply till whole, remains true. Again, with combustion analysis, the only difference is step 1 of the rhyme. Now, as combustion sounds, think, what are our products of a combustion reaction? Hopefully you said H2O and carbon dioxide. So, a couple of points to look at. Elements making up unknown substances always include carbon, hydrogen. Oxygen is often involved, and nitrogen is involved sometimes. You must know the mass of the unknown substance before burning it. So if I gave you 5 milligrams of some unknown, you need to know how much you're starting with. The unknown will be burnt in pure oxygen, present in large excess. Well, we want to make sure that we burn the entire unknown substance. So having pure oxygen with a large excess is we force the reaction to completely burn the unknown. And then with combustion analysis, the amount of oxygen present in the original unknown sample can only be determined by subtraction, which I will show you an example. So your products, as we said, carbon dioxide and water, NO2 sometimes also there. Nitrogen can also be N2, it could be ammonia, it could be N2O5. Nitrogen usually ends up being the problem child because nitrogen compounds from the reaction can be so many different things, whereas carbon is pretty much usually carbon dioxide. Hydrogen is pretty much usually water. Keeps it pretty easy when you're always the same compound, or usually, but nitrogen likes to show up as different things. One other thing to think about is, again, carbon is carbon dioxide, hydrogen comes as water. Okay, so first thing, determine the mass of each element present in the original compound. Again, this is the part that is different than the rhyme. Again, carbon is always carbon dioxide, arrives in the ratio of the mass of carbon to the mass of carbon dioxide. Hydrogen is always in water by the ratio of hydrogen in water to the mass of entire water. Notice it's 2.01 instead of 1.01 because we're not looking at one hydrogen in water, we're looking at 2 hydrogens per water molecule. Again, nitrogen can be many different things, and you always subtract to solve for oxygen. So you would take the sample mass given in the problem and subtract the quantity of the mass of carbon, mass of hydrogen, and if there is nitrogen, add that all up, subtract, whatever's left over is oxygen. Through subtraction, if you come up with an extremely small number, we usually can assume that it is 0 oxygen, and it's pretty obvious. And then, as I said, we continue with the rhyme from before. So I apologize for this being cut off. Not too sure why that's happening. So from here, mass to mole, divide by small, multiply till whole. It's a pretty catchy rhyme. So again, just kind of reiterating multiple times, we continue with the rhyme. You have the mass of each element from combustion analysis. So mass to mole, divide by small, multiply till whole. And that is pretty much it for empirical formulas. You have the homework with you. I passed out in class today. If you don't have it, you weren't in class. It is in the locker. Should be working on worksheet 1. Again, it's very straightforward. I think worksheet 1 is just regular empirical. There might be 3 or 4 questions on combustion analysis just to start the wheels going. And please bring some questions that you have to class, and we can go over some examples when you come to class. Thank you.